Hey, how's it going, everyone? Just wanted to make a quick video going over some Gen Chem 2 kinetics. Just a brief overview of probably the first question and the most tested question you'll get in your kinetics class or your kinetics section of your Gen Chem 2 class. Um, just to give a brief overview of what kinetics is basically the study of experiments and how their concentrations change and how their concentration change over a particular time. Now, a change of concentration over time gives us the rate of the reaction. And I want to point out a couple of very important things. So I'm going to show you here on my laptop here certain things. So let's start off with what the basic rate looks like. So basic rate law, for instance, rate law looks like this. It'll be rate is equal to K, which is our rate constant, with the concentration times the concentration, of a reactant to the power of M times the concentration of another reactant, B, to the power of N. Whoops, didn't mean to put a 6 in there, excuse me. Okay, so the basic rate law. Rate is equal to our rate constant K times the concentration of a reactant to the power of M times another reactant to the power of N. And in different circumstances, you may have more reactants. Sometimes the reactant concentration doesn't factor at all, we would see in a zero order reaction. But the one we will be dealing with here won't be a zero, or typically what you see in your class is nothing bigger than 2. So you usually deal with zero order, first order, and second order. You may get a question on your homework, which is third order. Finding them out or solving what their rate law isn't very much different from any other finding any other rate law for any kind of zero, first, second. So it won't be a big difference. The difference would come into when you were using the integrated rate laws, and for this class, we're only using integrated rate laws for zero, first, and second order. Moving on. So basically, this is our base rate law, and we need to determine the rate law for this set of experimental data. So we have the reaction 2NO plus Cl2 going to 2NoCl. So what we're going to do first is the easiest thing I would say is just write out all your experiments and plug in the values that you have here for your rate law. So we can easily do that. So we can start out first by using experiment 1 and using the rate and the concentration. So I'll do that. So I'll do experiment 1, shorthand notation, and then I'll do 3.4. Should maybe put a couple spaces in. So I'll do 3.4 times 10 to the negative 4 is equal to K, concentration of NO in this case, but in experiment 1 it'd be 0.0300 close parentheses to the power of M times the concentration which of Cl2 in experiment 1, which is 0.0100 close parentheses to the power of N. So this is our basic rate law. Now we'll do this 2 other times for experiment 2 and 3. Now, a huge misconception at the beginning is that we can simply plug in the coefficients in the equation for the M and N value. Do not do this. This is a mistake that usually happens in the beginning of learning kinetics. You do not want to do this. It's something that your professor probably won't appreciate it, because that means it's something you missed or weren't paying attention to in class, or you just simply forgot. It's a simple mistake that happens. I've done it probably once or twice in my in the classroom setting when I was learning this, but don't do that. M and N have to be calculated for. With that being said, let's write the other two experiments. So let's again do experiment 2, 8.5 times 10 to the negative 5 is equal to K. And then the concentration for NO in experiment 2, which is 0.0150 to the power of M times the concentration of Cl2 in experiment 2, which is 0.0100 to the power of N. And then finally, of course, we'll do experiment 3. I'll throw it down here under experiment 1. So we'll do experiment 3. Actually, let me do this real quick, space this out so we can differentiate it a little bit. So we have, again, 3.4 times 10 to the power of negative 4 is equal to K times the concentration of NO in experiment 3, 0.0150 to the power of M. And finally, the concentration of Cl2, which is 0.0400 to the power of N. So we have our three rate laws with data in them, inputted to them. And from here, we can start to solve for the order of each reactant. The order is basically like I was speaking about earlier, 0 first, second order. This tells us in terms of how the concentration is related to the rate. And these orders are dignified by M and N. Now, going back to algebra classes and many math classes, we can solve for variables like this. The only issue is that we have 3 variables. Now, in order to solve and to just figure out what the order is for each reactant and ultimately find out what the rate constant is, we need to begin eliminating these variables. Now, obviously, there's a relationship between the concentration of the reactants, or no relationship if we figure that out, but a relationship between the concentration of reactants, the exponents, the K, to the rate. And since these are all concentrations and rates of the same reaction, there's going to be a relationship between each reaction and each experiment. So what we can do here is we can actually use multiple, in this case two experiments in order to eliminate variables and solve for the orders, the exponents. The best way to do this is find experiments where one reactant has the same concentration and the other one has different ones. Now, that may not make a lot of sense right now, but once we do it, it'll make a little bit more sense. But for now, let's look at the experiments. So experiment 1, we have these concentrations. Experiment 2, we have these 2 concentrations. So right off the bat, in experiment 1 and 2, Cl2's concentration does not change. That's a good thing. We can eliminate this variable since it's the same. NO changes. So that means that variable won't be eliminated, so we can keep that. And the rates, they're different. It doesn't matter if they're different or the same, but they're different, so we can make that. So what we can do is we can actually divide the experiments by each other to eliminate the variables. Now, I personally like to use the bigger number up top and then followed by the smaller number on bottom. That just makes it easier to divide. It gives you whole numbers instead of fractions or decimals or something like that. So let's take experiment 1. Let's take experiment 1 here and simply divide it by experiment 2, like so. So if we actually do this, we'll get, so we can divide 3.4 times 10 to the negative 4 divided by 8.5 times 10 to the negative 4. If we do that, we end up getting 4. Nice whole number. Perfect. And then we set that equal to the rest of it. Well, if you divide k divided by k, we don't know what k is, obviously. K could be any number, but we do know that it's constant. So k divided by k will just cancel out to being 1, because you're dividing the same number by itself. So we can put in 1, but actually let's just leave it out, because any number times 1 is just the same number. So we'll leave out 1. Now we have 0.0300 divided by 0.0150. Okay. We divide that out and we get 2, but we still need to leave the exponent. Perfect. So we got 2 to the power of m. Okay, we got that. And then finally, we have the last reactant, but since it's the same number, it's going to be 1. So we're going to get 1 to the power of n. Now, we have eliminated k as a variable. Perfect. Now we're down to 2. We still need to get to 1 variable because, we can't solve for 2. It'd be very difficult to do. Here's the thing, though. With this value of the reactant being 1, n could be anything. N could be anything, and this is still going to be 1. It could be 100. It could be 1. It could be 0. It's still going to be 1. So effectively, we have eliminated we've eliminated the variable n because 1 to the power of anything will always be 1. So we effectively eliminated that. So now we're left with 2 to the power of m is equal to 4. Now 2 to the power of 2 is equal to 4. So from here, we know that m is equal to 2 because 2 squared is equal to 4. So m is 2. So the order of NO is going to be 2. So now what we do the exact same thing, but instead we want NO to be the same and Cl2 to be different in order to find the order of Cl2. So simply just take experiment 3. Whoops. Let's take experiment 3. Let's grab this bad boy, put it down here. And now we will take, experiment 2, because that's where NO is the same. So take experiment 2, grab it, divide it by each other. So what do we get? So 3.4 times 10 to the negative 4 by 8.5 times 10 to the negative 5 is, this should be 5, not 4. Sorry about that. Always be sure to double check your numbers. But anyways, 3.4 divided by 3.4 times 10 to the negative 4 divided by 8.5 times 10 to the negative 5 will still be 4. Perfect. Now we set that equal to, again, what's on the right side. K cancels again. K is gone. We know that 0.15 times divided by 0.15 will get 1 to the power of m, and that will effectively, we can neglect m because m can be whatever it can. We actually know it's squared, so it's still going to be 1, so we can still ignore it. Now we have 0.04 divided by 0.01. What does that end up being? 4 to the power of n. Whoops. 4 to the power of n. Now, the question is, what is 4 to what power is equal to 4? Well, that's simple. 4 to the power of 1 is equal to 4. So n is 1. So now we can write our rate law. Our rate law will be rate is equal to K. K. Parentheses, the concentration of NO to the power of 2 times the concentration of Cl2 to the power of 1. So that's our rate law. Perfect. First part in the bag, we got that. Now we move on to our rate constant. Our rate constant. Now, how would we do this? Well, if we look at the questions, the experiments we set up before, well, now we only have one variable now because we've found m and n, so the only variable is k. So you can pick any experiment and just plug in the values and solve for k. So for instance, we can use this one. Oh, whoops. So let me take experiment one, drop it down here, and determine the rate constant. So now we can just fill in the respective orders. Perfect. So now we have 3.4. So we have 3.4 times 10 to the negative 4 is equal to k. Now let's do 0.0300 squared times 0.01 to the power of 1. So we get the concentration of, or value of, 9 times 10 to the negative 6. Perfect. And then we divide this over. So we will take 3.4 times 10 to the negative 4 and divide it by 9 times 10 to the negative 6. And the rate constant we get is, k is equal to 30.78, and then we want to put the units, of course, so we'll do 1 over, this ended up being third order, so the units would be m to the power, m negative 2 times s negative 1. Now, so we have a rate constant, we have a rate law. Perfect. So now the final question I have for us, which is another question you will likely get, actually these 3 questions you will likely get for your first quiz, and it's likely going to be a good part of your exam. So last part is calculate the reaction rate when both NO and Cl2 are 0.0227. So those are the concentrations. So this last question, once you've done all this hard work here, is straight plugging it in and calculating it. So we know that our rate law, once again, is rate is equal to, typically you put k, but since we know it, we'll just put 37.8. Put that in parentheses to differentiate it. And then we'll do the concentration of NO, which is 0.0227 to the power of 2 times the concentration of Cl2, which is 0.0227. And since it's to the power 1, I'll just leave it like that. And since we have all the values we need, you multiply it straight across. And what you end up getting is the initial rate, or the rate is actually equal to, 4.4 times 10 to the negative 4. Now, rate is always recorded as m over s. M over s. Your k value units depend on the order. Since this was third order, it would be 1 over m to the power 2 over 1 over m to the 2 s to the 1. But rate is always measured as m over s. So that's all I have for you for today. I hope it didn't take too long, but how to basically go through an experimental data set and how to determine the rate law, rate constant, and how to find the initial rate when given new concentrations. So this will likely be on your first quiz, and it's definitely going to be on your test. So I would highly recommend to practice quite a bit of these problems, study up, and be sure you're ready. So once you just get there, you go boom, 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 fill it out, turn it in, get those good grades, and then have yourself a nice day. Be safe out there. I know it's been crazy with the coronavirus, but thank you for listening. Hope this helps, and take care. Have a nice day.